강의합시다. Okay, so today we will finish introduction and we will move to the branch prediction, which is the beginning part of the microprocessor pipeline. So this shows Intel i7 processor. The technology used for this processor is 32 nanometer process. So I think I have discussed this before. So as I mentioned, 32 nanometer process means the minimum feature size of the polygon. So this can be line width or length. The minimum you can fabricate using this technology. The minimum size is 32 nanometer. And it consumes about 130 watts of power. As I mentioned, this is about the limit of the maximum power budget for CPU design. If the CPU consumes more than this power, then it requires waterproof or other expensive packaging, which can increase the system cost. So you have to meet this power budget. Okay? Die size is 239 millimeter square, which is about 1 centimeter by 2 centimeter size. The clock speed runs at 3.46 gigahertz. It's 64-bit processor because i7 is based on x86-64, which is an extension of existing x86 instruction set architecture. So it uses the same instruction set as x86, but data size, the default data size is 64-bit. And this is 6-core processor, so each CPU chip contains 6 CPU. Each CPU has its own pipeline. And 12-threaded processor, which means they use hyper-threading. It's one of simultaneous multi-threading techniques. We discuss this multi-threading later. So every CPU, they have 2 program counters and they can fetch instruction stream from 2 different programs. Okay, so at the maximum, each CPU chip can run 12 different programs every second. Okay, it's not like old processors. In an old processor, only one CPU core and only one thread, one program counter. For this i7, there are 6 cores, and each core can execute 2 programs simultaneously every second. Okay, this performance is measured on spec CPU 2006. This benchmark is still the latest benchmark used for CPU performance, and the reference machine for this benchmark is 296 megahertz ultra spot. So assuming the performance of this machine is 1, this is relative performance. For integer or PC applications, it's about 159 times faster on average. Okay, the execution time is, they measure for spec CPU 2006, there are 12 integer benchmark and 17 floating point benchmark. Okay, so 12 programs and 17 programs. For each program, they measure the execution time in seconds. And they use UltraSpark 2 processor as your reference, as your comparison, and that's the relative performance of 1. Okay? And they measure the execution time for i7. So if this takes 1 second, i7 takes 0.5 seconds, then its performance, relative performance is 2. Okay? Because its performance is expressed as a ratio of execution time. Okay? And they measure this ratio for 12 applications, and then they take the geometric mean, because these are the ratio. If you take, they don't take arithmetic. So we discuss how we calculate this variations. For floating point application or server application, it's about 103 times faster. And the core pipeline for each of these core, each CPU, each processor core, is the new design and is derived from Pentium Pro microarchitecture. So Pentium Pro uses 10-stage 3-issue out-of-order superscalar pipeline. So they modify this pipeline, and this is actually 14-stage 4-issue. So pipeline stage has been increased, but not as much as in Pentium 4. And this is 4-issue stage, so they increase IPC, and it's also out-of-order pipeline. They optimize this pipeline for multi-core support and try to reduce the power consumption compared to Pentium Pro pipeline. And it's 64-bit, x86-64. So Intel has two different 64-bit machine language. One is this x86-64, and the other is IA64. Okay. And they have three different versions: for i3 for entry level, i5 for mainstream, i7 for high end, and Xeon is the brand name for the server. So this shows the most performance, highest performance among the variations. For each core, it has 256 kilobyte L2 cache. This is per core, so for 6 core, you have to multiply by 6 for the total L2 size, and they can have off-chip up to 12 megabyte L3 caches, and they integrate memory controller on chip, which means the memory controller function, they translate the address provided by processor, they take the address and they translate to memory address. Memory chip, they use multiplexed address line. So instead of 32-bit address, they translate it to row address and column address, two-dimensional access. Okay, so they maybe from 32-bit address, they take first 16-bit for row address, and then next 16-bit for column address. Okay, but this kind of logic was in off-chip chipset, but they moved to on-chip, and they removed the system bus from the system. So if you look at i7, the computer system based on i7, there is no system bus. Before i7, they used to have system bus, and system bus was called CPU bus or host bus or front side bus. They are the same terminology. So for the same system bus, CPU bus, host bus, or front side bus, they are the same. The bus is a transmission line, as I think I have discussed for most of you, but let me repeat. Bus is quite slow because of the characteristics of its transmission line. So if you have a driver and bus, you have to drive multiple chips or multiple roads. For CPU address bus, this kind of system bus address bus line goes to each DRAM chip. So if you think about DIMM module, DIMM card, memory card, it's dual in memory module DIMM. They have 8 chips front and 8 chips in the back. So they have total of 16 DRAM chips. And these DRAM chips work together in parallel. And each DRAM chip produces 4-bit data. So you have 64-bit system bus. So you provide address, and then each bit provides 4-bit times 16 chips. So 64-bit data are transmitted every cycle. That's the maximum you can transmit because there is only 64-bit data bus line. So essentially, each address bus line, transmission line, has to drive 16 DRAM chips. And if you increase this chips, number of chips, then it will be heavier to drive because you have to drive many outputs. Okay? So the switching time is quite slow because you have to drive many chips, which means it's heavier and the switching time is slow. Because of this bus transmission line characteristics, compared to processor clock speed, bus speed has been increased only marginally compared to processor clock speed. In 1980s, in the PC, the system bus clock speed and CPU clock speed was about the same. But nowadays, CPU clocks run at more than 3 GHz, but the system bus still runs at 200 MHz or something like that, very slow. And they try to come up with other technologies such as double pumping or quad pumping, which means every bus cycle, before the signal arrives at the destination, we send another signal. It's called bit pipelining. And they try to increase this bandwidth, but still the bus clock speed is quite slow because of this structure. And nowadays, due to this problem, all the bus technology has been replaced by point-to-point interconnect, which means there is only one driver, only one load. If you try to connect multiple loads, you have to connect like this way. So each transmission line needs to drive only one load, which means it's much light. Okay, so you can drive quickly and you can switch it faster. So clocking speed has been increased by this point-to-point connection. This has been applied to this new technology called quick path interconnect. This is serialized using this point-to-point processor interconnect. Also, PCI Express uses this kind of point-to-point interconnect, and the disk interface called SATA is also based on this point-to-point interconnect, and so they are all changing to this point-to-point interconnect to increase clocking speed. If you increase clock speed, you can increase bandwidth. Okay? So if you use this kind of technology, yes, interconnect clocking rate can be increased. So as before, there are two chipsets. This is north bridge, this is south bridge. But the functions are different. Usually, the memory chips were attached to this north bridge chip before, but they moved to on chip. The memory controller is inside this function, and they support up to 3 channels, and you can control DIMM card directly from the CPU using this point-to-point connection. It runs at 3.2 gigahertz clock, but actually, this clock speed is about 1.07 gigahertz, and there are 3 channels. So total is like runs at 3.2 gigahertz, and so each channel is 8-bit point-to-point connection. So 3.2 gigahertz times 8 byte, it gives you 25.6 gigabytes per second, which is much faster than before, much faster than traditionally the maximum front-side bus that they can implement was 1.6 gigahertz. This is actually now 1.6 gigahertz. The system bus runs at 400 megahertz, and they use quad pumping, which means each bus clock speed they transmit 4 signals using big pipeline. And using this technology, they can double the bandwidth of this interconnect bandwidth. And they support 32-bit physical address, which means their maximum DRAM using i7, maximum DRAM size or maximum memory is only 64 gigabytes, even though they are 64-bit processors. Address size is not always same as data size. Okay, for 32-bit processor, they used to implement 32-bit address. So for Pentium Pro, they support 32-bit virtual address and 32-bit physical address, which means 32-bit virtual address means the program can be as large as 4 gigabyte. 32-bit physical address means the DRAM main memory can be as big as 4 gigabyte. But for 64-bit processors, since address is also a kind of data, intuitively, the address size should be 64-bit. But if you implement 64-bit address, then in the pipeline, the 64-bit address bus takes too much space because this is too wide. Okay, but for physical memory, main memory, 64-bit physical address is not meaningful because there's too much memory space. Okay, 64-bit is 30-bit address means gigabyte, 40-bit address is terabyte. So more than terabyte physical memory or main memory is only for supercomputers, not for servers or PCs. So you don't have to implement that wide address bus. That's why they reduce this address bus, to reduce the chip size, die size, because this interconnect takes space. Okay? So this key path interconnect is based on this point-to-point connection. It's replaced the existing, the old front-side bus or system bus. This key path interconnect can transmit 64-bit data every 2 clock cycles. And it can give the same speed as this memory interconnect to 25.6 gigabytes per second. Okay? So if you want to connect multiple CPU, you have to use key path interconnect and so on, using point-to-point connection. So the structure is a little different, but eventually it can give you higher communication bandwidth. This is important because even if you can design a CPU that gives you very good performance, if you cannot support good system bus bandwidth or communication I/O bandwidth, then it will be saturated by this communication. So it will be most of the time the CPU is waiting for memory because they can transmit only little, right? So if you want to increase your total computer performance, as much as you increased CPU performance, you have to increase I/O chip bandwidth or system bus or interconnect bandwidth as well. Otherwise, the other components will be a bottleneck. Okay? So they realize they cannot no longer sustain the slow speed of this bus, and they are replacing this bus, eliminate all this bus structure, and all these connections are based on point-to-point interconnect nowadays. And this, so this has PCI Express bus connected, and this is another interface that connects this north bridge chip to south bridge chip, and this is another new interface called direct media interface. This is the link between north bridge and south bridge chip, but this is about the same as PCI Express. They share many characteristics of PCI Express. PCI Express is also point-to-point interconnect that replaced existing PCI bus. PCI bus was like system bus. It was slower than CPU bus or system bus, but it's another bus structure. But because of bus limitation, they replaced with PCI Express standard, which is point-to-point connection, and this is similar to PCI Express. And to the I/O controller hub, this south bridge chip, you can connect hard disk drive such as SATA interface and another PCI Express or USB and so on, or networking. Okay, let's look at other microprocessors. This shows Sun's UltraSpark T2. The code name was Niagara 2. It's the CPU clock runs at 1.4 gigahertz, but each CPU chip contains 8 processor cores. So it's multi-core than i7, and each core is 8-way multi-threaded. That means each core there are 8 program counters. You can fetch instruction stream from 8 different programs every cycle. The total there are 64 programs that can be run at the same cycle, every cycle from this CPU. Okay, so each CPU, the CPU chip can run 64 different programs every cycle. The fabrication process they used was 65 nanometer process and 1831 pin. So they should use much. They use more number of pins. They use more number of address lines and data lines to speed up their communication. Okay, I/O to increase their I/O pin bandwidth. So it means it's quite expensive packaging and more expensive system design. It contains about 500 million transistors, consumes 84 watts of power. Okay, and each core here is 2-issue 8-stage pipeline. Right? So they provide 4 megabyte L2 cache. It has 8 banks. So each core has 1 bank. So if you look at this core, there are 8 cores, and each core is connected to this L2 cache bank. And memory controller are also integrated on chip and is connected to this DIMM memory card, and it's fully buffered technology. It's trying to increase also point-to-point interconnect. And buffered means they can send directly from the CPU, but they are buffered, and then they are transmitted at the maximum speed using the point-to-point connection. And it can provide more than 60 gigabytes per second memory RAM. So this is for servers. The core, CPU core might be slower than i7 core, but it's more multi-threaded and it's more multi-cores, and they have higher I/O bandwidth, so they can provide higher memory bandwidth in general. Okay, and they use full crossbar to connect each CPU to different L2 bank. So, like i7, they also remove all this point-to-point bus connection. Okay, they use based on point-to-point connection. This was announced earlier than i7. This is more old design, and they have a new chip called i7 T3, and the code name is label for Victoria Falls, and they use 40 nanometer process. They increase processor core number to 16, and the clock speed has been increased a little bit, 1.65 gigahertz, and so you can run 128 programs every cycle. Okay, so if you look at textbook, there are some performance comparison between UltraSpark processor versus AMD Opteron processor, which is another x86 based 64-bit processor. So you can compare performance. It depends on application. Let's review some trends in technology. So we are using this textbook. So most of the slides I made it by myself. So some of the pictures are from the paper I'll add some of the content from this textbook. Okay? Let's see. So these are the contents from the textbook. So how the technology trends are going. Transistor density has been increased about 35% per year. Die size is also increasing, so the chip size is becoming bigger and bigger. So if you combine them, the IC integration density is increased about 40 to 55% per year. Okay? That's the overall integration scale. So every year we expect about at least 50% growth in the number of transistors per die. DRAM capacity is also increased about the same as this transistor density, 25 to 40% per year, but it's been slowing down a little bit. So in general, it used to follow more slow, but a little bit slower than more slow nowadays. And Samsung actually predicts once low, they expect they can double the this density every year, but that's only for a short period. Nowadays, it's slowing down further. Flash memory, this is EEPROM. The capacity is increased faster, 50 or 60% per year. It's about approximately 20 times cheaper than DRAM. Disk technology, the capacity has been increased about 40% a year. It's another 20% cheaper than flash. So overall, disk is about 300 to 400 times cheaper. So 20x between DRAM, flash, and disk. 20x, 20, so about 400 times. Okay, cheaper but slower. Okay, that's the technology trend. And this technology trend. 안 들리나?
녹음한
좋아. So technology trend, you can view them. One is in the bandwidth trend, and the other is latency trend. Bandwidth, or sometimes it's also called throughput, is total work done in a given time. So for communication, it can be bytes per second, or for performance, computer system performance, it can be number of instructions per second. That's the bandwidth. How many instructions you can process per second, or how many data, how many bytes you can transmit every second. Okay? Latency is the time between the start and completion of an event. So it can be, for DRAM, you provide an address, and then after you do a row access and column access, the data is available at the output. This is the total access time for this DRAM chip. And this is the latency. Okay? And in general, for the general technology trend, this bandwidth, you can improve bandwidth much faster than latency. Latency is hard to improve. So only a small increase in the latency performance, but the bandwidth you can usually increase. There is more ways of improving the bandwidth. So this shows relative trend between latency and bandwidth. So this is same. If the latency and bandwidth is the same, they will follow this line. But if you look at these four different technology, processor, network, memory, and disk, all these technology, they have improved bandwidth than latency because their curves are steeper than this latency bandwidth improvement. This is, if they are about the same, they should follow, but they can improve more bandwidth or throughput than latency. Okay? And biggest performance gain was achieved by processor, so more than 10,000 times, right? For the last about maybe 20 or 30 years. So this picture you should look at with tables in the textbook. So where is my, okay. Did you buy this textbook? No? You should buy, you have to read. These are, two persons are maybe the most famous person in computer architecture or in computer science and engineering in general, okay? So in the textbook you have this picture, you have to look at this table below. It just shows how this technology trend has been going for last 20 to 30 years. So this is some kind of technology milestone. So for processor, this diamond shows some kind of milestone. And the latest one is for Intel Core i7 processor that we have discussed. And the first one was for 16-bit processor, that's 286 processor that was introduced in 1982. Okay? And how this performance has been increased. And if you look at latency in MIPS, million instructions per second, this 286 processor, this is 16-bit processor, its maximum bandwidth or throughput is 2 MIPS, 2 million instructions per second. Okay? And this i7 processor, its bandwidth is about 50,000 MIPS. So that's about 50 kips. 50 billion instructions per second. If you compare, that's about 25,000 times growth in terms of throughput. So this shows about 25 times. Okay? But during that time frame, the latency is less than 100. Okay? If you look at latency, so this 286 processor, the latency, I'm not sure which latency is discussing, but it shows the latency is about 320 nanosecond for the latency. For i7 is 4 nanosecond. So this might be some maybe integer operation or might be some other operation latency or floating point. I'm not sure. So 320 to 4. So latency has been reduced by about 80 times. So this is about 80 to 25,000. So latency has been increased very slowly, but the throughput has been, or bandwidth has been increased substantially. Okay? Let's look at the memory side. The bandwidth, so memory, this one. The first DRAM chip they used was announced in 1980, and in terms of is 64K bit DRAM. 64K bit DRAM. The latest one is 2 gigabit DRAM, DDR3, synchronous DRAM. So in terms of bandwidth, the first one is 13 megabytes per second bandwidth. The last one is 16,000, so 16 gigabytes per second. So 16,000 divided by 13. So it gives you how much? About more than 1,000. Okay? Memory more than 1,000. For latency, the DRAM access time, this was 225 nanosecond for 64 KB DRAM. Nowadays, the latest 2 gigabit DRAM chip is 37 nanosecond. So 225 divided by 37. So approximately 6 overall DRAM access has been improved by 6 times. So this corresponds to about 6. Okay, and so on. So latency is has been improved slowly, but the bandwidth has been improved substantially for each of these technology. Okay? The feature size has been in 1971 it was 10 micron. Nowadays it is for year 2011 32 nanometer. This is actually 0.032 micron, which corresponds to 32 nanometer process. And nowadays it's about 22 nanometer process, the most recent one. Okay? And if you reduce this minimum feature size, which means wire length or width, okay, transistor performance usually scales linearly. Okay, if you reduce by half, their performance is also reduced, increased by twice. And integration scale, density scales quadratically, assuming two-dimensional design. But actually, it's three-dimensional because you have multiple layers of metals. So it's more than quadratically increased. So density is increased more than quadratically. Transistor performance scales linearly, but wire delay does not improve with feature size. It's actually slowing down. This is an old slide. I sent you the slide yesterday, last night. 동호, 오래된 거 같은데? 옛날 거. 가장 최근 거야? 이거 아마 그 윈도우 프로블럼 내가 같은 곳에서 하면 옛날 게 올라오는 그 문제인 것 같은데. 그래. Okay, but the issue is this one, wire delay. Wire delay. Even though maybe the switching time is much faster as you decrease your feature size, but the problem is wire delay. Wire delay does not scale as much as transistor performance. And the wire delay becomes a problem. Wire delay actually depends on RC, resistance and capacitance. And if you consider this complexity, even though you decrease your feature size, the wire delay is increasing compared to other characteristics. That does not scale well with feature size. So nowadays, the two most important issues in IC design is one is wire delay, the other component is power consumption. Those two are the limiting factor for IC design and processor performance. Okay. Okay, let's review power. For CMOS chips, traditionally, dynamic power is the dominant energy consumption source. Okay, you can divide power consumption in dynamic power and static power. Dynamic power means switching power. You turn it on the transistor, you turn it off. And whenever the transistor is switching, the current flows from VDD to ground. It consumes power. That's the dynamic power consumption. And this dynamic power consumption is expressed as this equation. It's called C V square F. So power consumption is proportional to frequency, but quadratic in terms of voltage, and it's also scaled with capacitance, how many loads you have. So for a fixed task, for the same task, if you slow down your clock speed, you can reduce power consumption, but not energy. Power is the energy consumed per time. Okay? So if you decrease frequency, you run the clock slowly, and the power is linearly reduced, but you have to run the program proportionally more, right? To finish the job. That means the total energy is the same, even though you reduce the power. Power and energy are different, right? So if you run your CPU clock at 1 gigahertz, you can finish in 1 second, the same job. If you run at 500 megahertz, you require 2 seconds. Okay? So power consumption is reduced by half because the clock speed has been reduced by half. But because lower clock speed, you have to run it twice longer, which means total energy consumed by the task is the same. Okay? But the advantage is if you reduce this frequency, sometimes you can reduce the, this voltage as well. Okay? But if you reduce the voltage, then you can effectively decrease this dynamic power consumption because it is proportional to voltage quadratically. Okay? So they are trying to reduce this voltage. So if you look at this operating voltage, the IC chip, it's been going down. So from 5 volt, it's around 1 volt nowadays. And capacitive load is a function of number of transistors connected to the output. So it usually depends on how many gates you have, how many transistors. It depends on the size, the volume. So to save energy and dynamic power, what you can do is, first you can do voltage and frequency scaling, which means you can decrease your frequency and at the same time you can decrease your voltage. Then you can decrease your power consumption and energy consumption. And the other method is you can turn off the clock of inactive modules. So in the CPU chip, if the floating point, if you are not doing any floating point computation, you can turn off the clock to the floating point unit. Then there will be no dynamic power consumption. From the floating point unit, you can reduce the power. Okay? Let's look at this voltage and frequency scaling, how you can reduce the power consumption. Let's say, suppose that you decrease your frequency by 15%, and usually you can decrease your operating voltage also by 15%. Then what you can do is dynamic power, the voltage becomes only 85%, and the frequency becomes 85%. If you multiply this, then even though your performance has been reduced by 15% because you reduced the frequency by 15%, the power consumption has been reduced by 40%. 40%. Okay, so it's quite effective. So that's why notebooks or the PCs are using this dynamic voltage and frequency scaling. Okay, if there are not much application running, then you can reduce your frequency and you can reduce the power consumption more effectively. Then in performance reduction. So, as an example, maybe I can ask you why multi-cores are more effective in low power consumption than single core processor. Let's say you have 1 gigahertz CPU. The other option is you can have 2 cores runs at 0.0 gigahertz, 500 megahertz CPU. Okay? In terms of throughput, they are the same because you have either twice the performance or single performance but twice as many. Okay? So compare the power consumption, dynamic power consumption between the single core versus multi-cores by yourself using this equation. How much you can reduce? The assumption is if you reduce the clock speed, you can also reduce the voltage as well. Okay? Operating voltage. Compare the dynamic power consumption between these two chips. What is the ratio? To the exercise. 계산해봐. 머리 좋은 사람은 암산으로 하고. Yes. 다 계산했어요? Have you done? Are you done? How much you can reduce? By half? Is it right? So, what is your name? Auran? Auran Godib. Okay. So you said this single core, dual core can reduce dynamic power by half. Okay? Any other answer? Hmm? 1/4. What is your name? Teu. Maybe Teu Lee. And this is Dao. Daogram or something like that. Sorry about your name. Dao Rango. Let's do a poll. You can reduce power consumption by half. Raise your hand. Raise your hand. Okay, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. By 1/4. Raise your hand. 1/4. Two? Two? How about you? No idea? Okay, let's do a simple calculation. Okay, so it's CV square F. Okay, original power consumption. Let's say this one is dynamic power is CV square F. Let's compute the power consumption for this one. So dP dash equal C V square, which is V square dash E분의 1 F. Right? The assumption was as much you reduce the frequency, you can reduce the operating voltage. So it will give you, right? You have two cords. So total chip for this power consumption is 2 times. So it's about, right? So you can reduce the power consumption by 1/4 if you use half clock speed dual core. Okay? If you use quad core or A core, you can reduce it further. Okay? That's the advantage of multi-core or parallel processing. In terms of dynamic power consumption, parallelism or multi-cores are better. Okay? So theory, I'll give you 5 bonus points. Okay? 이쪽은 어떻게 된 거야, 이거? 산수도 못해, 산수? 수학도 아니고? 보자, 어디 있나? 오케이. Let me check whether I have some more updated ones. This one is also old. Okay. Maybe there was a mistake when I send you. Okay, let's review static power. So power consumption can be divided into dynamic component and static component. Dynamic component means switching power. Static component means leakage power. Okay? Even though you don't do anything, there is a leakage current flowing from VDD to ground because the semiconductor transistor is not a perfect switch. Okay? So you can view this transistor as a switch. For example, for DRAMs, for NMOS transistor, if the gate is high, then you turn on the transistor. Then the current flows from here to here, VDD to ground. If the gate voltage is low, 0, means this switch is turned off. So it's essentially a switch. Okay? So all for CMOS logic, or most you can view them as a switching logic. You can implement NAND, NOR using this switching characteristics. But the problem is, this is a semiconductor. It's not a perfect switch. Even if you supply 0 or low voltage to this gate, then the transistor was supposed to be turned off, but there is a leakage current flowing. Okay? So that's why you need to refresh for DRAM, because even if you have high voltage at the output and you store your 1 in this cell as times go by because of leakage current. If you look at this V out will eventually from the high, slowly it will be low because of the leakage current. So what do you need? You need to recharge back to high. This is called refresh. And this kind of current flowing causes this static power consumption. But the problem is, as you decrease your feature size, the leakage current is usually relative portion of this static power is increased. So in old technology, this was not a major issue. But in recent IC technology, this static power consumption becomes significant. So in 2006, leakage power or static power consumes about 25%. For high-end design, it's around 40%. Nowadays, I'm not sure, maybe half and half for maybe the most advanced high-performance design. So static power, you have to reduce also. Okay, so there are many techniques to reduce this static power in computer architecture papers and also circuit and logic papers. So they sometimes gate voltage to inactive modules to control loss due to leakage. So there are different ways of reducing the static power. So sometimes VDD signal, there are VDD supplied to these cells, and VDD is also can be gated. Gated means can be gating means using other transistor you can turn off the power to the VDD so that there will be no current flow and so on. Okay. Let's review processor performance equation. So how you can measure the performance? You measure the execution time. To complete that application, how long does it take? Execution time can be expressed as 3 components. This is number of instructions per program, or program size. This is clock cycles per instruction. This is clock cycle time. Okay? And if you multiply these 3 components, it gives you execution time. So time equal how many instructions you have to learn to complete the program. Okay? And then for each instruction, how many clock cycles do you need to complete one instruction, each instruction? Then times how many seconds for each clock cycle. This is number of instructions, this is CPI, this is clock cycle time. Then if you multiply them all, instruction, clock cycle cancel out. So how many seconds for each program? Okay? That's the execution time. So to increase your performance, you have to decrease your execution time. To decrease your execution time, you have to decrease your program size. That means it depends on the compiler. So, okay, how you produce the instruction. If you generate a small program, then you have less number of instructions to complete. Then the program will finish earlier. Or you have to decrease your CPI, or you have to decrease your clock cycle time. Inversely, you have to increase IPC. IPC is inverse of CPI. How many instructions per cycle you can complete. Or you have to decrease your clock cycle time, or you have to increase your clock speed. Okay? So for processor performance, you have to look at three components: program size, or IPC, or clock speed. In general, when you compare two processors without computer architecture knowledge, you only look at the clock speed. So 3 GHz CPU will be always faster than 2 GHz CPU, but that's not true. You have to look at IPC. IPC means instructions per cycle. So compared to 486, which is a single issue processor, maybe Core 2 microarchitecture used for i7, that's 4 issue. Every cycle you can fetch and learn 4 instructions. This one should have higher IPC because it processes 4 instructions every cycle, every pipeline stage. Okay, you have to compare the IPC, and also you have to compare the program also. If you have same program, if two processors, let's say one is Pentium Pro, the other is maybe ARM, strong ARM. Assuming they have same clock speed, okay. One is, let's say, ARM, and the other is Intel processor. Same clock speed, same IPC. Okay? Because today's recent ARM processor also they use dual core or triple issue. Okay? They are resembling microprocessor of Intel's microprocessors. But which one will you choose? If you have ARM processor and if you have Intel processor, the same IPC and same clock speed, which one should be better? Let's remove this ARM with digital alpha processor, which was the fastest microprocessor in the world before Intel announced the fast one. Okay. Alpha processor is a RISC processor, 1 gigahertz, maybe 4 issue. Okay. This one i7, 4 issue. Both of them are 1 gigahertz. Same clock speed. Which one is better? Alpha or Intel x86? Which one will you choose? DEC alpha, let's say 2 gigahertz, and this one has maybe 2 IPC, this is 4 issue, and let's say Pentium 4, 2 gigahertz, this is 4 issue, but this is 3 issue, and somehow, because Pentium 4 is a new design, they also achieve 2 IPC using maybe their larger cache, better branch predictor, and so on. So they have same clock speed, same IPC. Okay? The question is program size. Which one will you choose? Alpha, raise your hand. How many? 1, 2, 3, 4. Pentium 4, raise your hand. Pentium 4 should be faster. 1, 2, 3, 4, 5, 6. Which one will you choose? 용수. 몰라? 그냥 수업을 이렇게 건성으로 들으니까 그렇지. 응? Pentium 4 should be better. So, Pentium 4, raise your hand. Pentium 4. You win. Because Pentium 4 is a CISC processor. Alpha is a RISC processor. CISC processor means it's complex instruction set computer. It provides more number of instructions. Each instruction is complex. So you can express complex operation using a single instruction. In a RISC processor, even though RISC processor, because of the simplicity, usually you have higher clock speed implementation is more possible. But using a RISC instruction, one CISC instruction corresponds to maybe 1 or 2 or 3 couple of RISC operations. Because RISC instruction means small number of instructions, and each instruction is quite simple. So to express a complex operation, you need 2, 3, or 4 RISC instructions instead of a single one. Okay? But the assumption was they used the same clock speed, same IPC. Then program size, the CISC Pentium 4 programs will be smaller. Usually, compared to RISC architecture, CISC architecture, program size is usually about 30% smaller. Okay? So you should choose Pentium 4. Okay? So as I said, you have to look at 3 components together to compare the performance. IPC, clock speed, and the program size. Okay? Okay. Let's review some of these power dissipation problems. 386 processor, this was the first implementation of i32 processor, this first generation 32-bit Intel processor, consumes about 2 watts. Recent i7 consumes 130 watts. This is the power limit that can be cooled by air. Because if you exceed this, the heat problem is too much. It's too hot. It causes lots of problem. It increases your packaging and system costs because you require some expensive cooling technology such as water cooling if your CPU spends more than this power. And also, if you increase this temperature problem, then the reliability problem occurred. So if you increase your chip temperature by 10 degrees in Celsius, your reliability drops down by half, usually. Reliability means bit errors. So if you read or if you do a computation, there can be an error because of this temperature problem. Okay? So this is the maximum power budget for processor design. So clocking rate has been increased exponentially, right? So during this period, 96 to 2002, they follow approximately more slow. Okay, clocking speed has been increased exponentially. But after 2002, it's been slowing down. Pentium 4 was 3.2 gigahertz. The new one, D1 is server version for i7, runs at 3.3 gigahertz. Only marginal improvement, no improvement at all actually, because of this temperature and the power consumption issue. Okay? Let's look at the performance. Performance can be expressed by inverse of the execution time. If your execution time is smaller, then your performance is higher. Okay? So X is n times faster than Y means its performance is n times faster. Inversely, execution time is n times shorter. Okay? Performance, how to measure? Usually you rely on benchmark instead of real workload, because real workloads there are so many variations. You cannot measure the performance of all the applications. So instead, you select a common set of most commonly popular application for that computers. Okay? So to increase product predictability, instead of a single application, single benchmark, you choose a collection of benchmarks. So it's called benchmark switch. Okay? So you have two switches. One is for CPU performance, we have spec integer 2000 benchmark switch and spec floating point 2000 benchmark switch. For spec integer 2000, there are 12 integer applications. For floating point, there are 14 applications. For spec 2000, there are 12 integer and maybe 17 floating points. Okay? These are the benchmark. Okay. This is spec 89, 92, 95, 2000, and 2006. And the long-lasting one is this GCC, GNU compiler. It was used in spec 89 all the time through 2006. All the other has been gone. Okay? So these are the current one. So they use GCC, Perl, MCF, bzip2, Go, and so on. These are 12 integer applications used by spec integer benchmark switch. And these are floating point benchmark. So you have computational fluid dynamics, numerical relativity, finite element, differential equation, quantum chemistry, and so on. So most of these applications do lots of floating point computation. So that's why these benchmark applications are called floating point benchmark. These are called integer benchmark to compare. Okay, this is for PCs, this is for servers and mainframes. Okay, and this kind of gzip, these application has been removed and it's been replaced by these new ones. And some of them are still lasting 2006. Okay, and this has been replaced by these. So these are all new ones, right? Okay, this is for CPU performance, so it's called spec CPU. And for server, you use TPC. TPC stands for Transaction Processing Console. And there are 4 different benchmark suites. TPC-C for query for online transaction processing. TPC-H for ad hoc decision support for management systems. For TPC-W for web. TPC-App for application or web server. Those benchmarks. Okay. How to summarize performance? If you take arithmetic average of execution time, that's not good, because if you measure the execution, it depends on application. Most of the application can finish in 1 second. Assume that 1 second, 0.9 second, 1.1, and so on. But one application takes 100 seconds. Then, if you take the average, the machine that takes the shortest amount of time in this longest application will have benefit, because it will be biased by this long-lasting one, right? So arithmetic average is not good on. So instead, how do we do? You can add a weight for each program, for each application, but different company want different weight for their product, because some machines are good for this application, some machines are good for the other application. So instead, they normalize execution time to a reference computer, as you have discussed. So you measure the execution time on the reference computer and the machine, and this ratio gives you the spec ratio. So if the reference machine should be relatively 1 or 100, depending on the benchmark suite, right? So you measure the execution time 1 second. You measure the execution time on your machine 0.5 second. Then your performance should be 2, right? Because the execution time is only half. Okay? So spec ratio on computer A is 1.25 times bigger than computer B, which means about 25 times faster, 25% faster. You can express this way: 1.25 spec ratio A is higher than spec ratio B. Spec ratio is expressed as this: execution time on the reference machine divided by execution time on the machine A. Okay? If you do this calculation, execution time reference will be cancelled out, and this one will be inversed. So execution time A versus execution time B, which is actually performance B, A divided by performance B. Okay? So this 1.25 shows relative performance of A compared to B. So when compared to computers as a ratio, execution times on the reference machines are dropped out or cancelled. So the choice of reference machine is irrelevant. Okay? Even though you are using reference machine. So you can compare the machine performance relatively to any other machine using this spec ratio. Okay? Since you use ratio, proper average is not the average mean. You have to take the geometry mean, which is this. Okay? If you have 12 applications, and it should be 12, you multiply all this ratio, square root, not the square root, and square root of the ratios. That should give you the spec. Okay? So maybe in the exam, if I give you simple questions, I'll give you execution time on different computers, and I can ask you what are the spec ratio. Okay, you can come up with this kind of simple calculus. Okay, and actually this is called spec ratio, and there are also called spec rate. Spec rates are for, this is for single program performance. Spec rates are for throughput, such as multicoor or multithreading. You can measure also throughput, how many total number of instructions you can complete instead of a single program performance. So there are the different measures. We'll discuss that issue maybe later when we discuss multithreading. Okay, exercise 3.2 GHz Pentium 4 processor is reported to have spec ratio of 1221 for iSpec and 1252 for floating point. What does this mean? Okay, this means compared to a reference machine, which is a 300 MHz ultra spot, integer performance is about 12 times faster because for spec CPU 2000, the reference machine's relative performance was 100. So 1221 means it's about 12.21 times faster than reference machine for integer application, and floating point is also about 12.5 times faster. Okay? How much memory can you address using 38 bits of address? So if you use 38 bits of physical address, that means your maximum main memory DRAM size can be 256 megabytes. If you use 36-bit virtual address, your program can be as big as 256 gigabytes. Okay? The virtual address determines the program size, physical address determines main memory size. Okay? Classify Intel's 32-bit microprocessor in terms of generation. So we classify them already. 386, first generation, 486, second generation, Pentium 4, fifth generation. The meaning of generation here is the microarchitecture. It's the internal design. To the programmer, they are the same machine state, same instruction. You can program in the same way. So all the programs are comparable. The 386 programs can still run on Pentium 4, but their internal designs are different. Sometimes they can use pipelining, superscalar, out of order, and so on. Assuming two processors, one RISC, one CISC, same class speed, same IPC, which one should perform better? CISC should perform better. Okay? And actually, I have some homeworks from the textbook. It's in the new slide. So maybe I'll update the new slide in the homepage. So you have to look at the homepage and send me your homeworks by next week. So this homework is for your exercise, not for grading. So I'll just check whether you submit your homework or not. Okay? So just submit your homework. I'll not provide solutions because it's prohibited by the author. Because once you provide solution, then it will be everywhere. Okay? And for the exam, I will ask you some of the exercise from the textbook as an exam question. Okay? So do your homework for your exercise. Okay? let's have a break and we'll come back in maybe 10 or 15 minutes.